Okay, so now, before we start, okay, we do know that enzyme, they are very, very specific. Okay, so this is due to what? Due to the foldings of these polypeptides into very precise three-dimensional shapes. Okay, so this one we have learned previously. Okay, now when these polypeptides fold into the precise three-dimensional shapes, then you do have this what we call the binding site. So something like pockets. When you fold something, you have the pocket, okay, here and there. So one of the important domain or the pockets here is termed as active site. Okay, so what's the active sites? Active sites of an enzyme is known as a groove or pockets on the surface of the enzyme where the reactions of catalysis occur. And this groove is very, very precise. Okay, so we say the enzyme is very specific. What? Because of this, highlight the words complementary. Okay, fits between the shape of its active sites and the shape of the substrate. This is very, very important. We use the word complementary. So when you describe the mode of actions of the enzyme, when we talk about specificity, we have to understand that. Okay, if this is enzyme, and this is active site, and if this is my substrate, so you can see that students always use the wrong term here. Make sure that you use the correct term. Okay, now what I mean here is, look at this. The shape, this is the shape of active site. This is the shape of substrate. And you can see that both of them, they don't have the same shape. Can you see that? They don't have the same shape. Are you clear? So this kind of the interactions of formations, okay, we say that the shape, okay, the word shape must be there. The shape of active site is complementary to the shape of the substrate. Are you clear? Can you see that? Complementary, the word that we use. Okay, it's not the same, don't say similar. Are you clear? And the word you must put in here, shape. It's not active site with substrate. What complementary? Mass, volume. So in this case, it's a shape of active site is complementary to the shape of the substrate. So this is very, very important when you answer the question. So it means that only the substrate which have the complementary shape to the shape of the active site can fit into the active sites. So once this substrate bind with the enzyme, it form what we call the enzyme substrate complex, and the catalytic reaction take place at the active site, allowing products to be formed. Are you clear? Okay, so when substrate bind the enzyme, it form the enzyme substrate complex, and then a series of things take place. Okay, a series of things take place, and therefore products can be formed. Okay, so this is what I mentioned here. Can you see that? The substrate bind to the active sites. So the shape must be complementary. Okay, and then the shape, the bonds in the substrate are weakened, are broken. Okay, let's say this is glucose, this is another glucose molecule, or sucrose molecule, for example. We can break the bond so that it form the products. So the intermediate stage here is termed as the enzyme substrate complex, or ES complex. Okay. So how enzyme can actually, okay, carry out the catalytic process? Then we have to look at the mode, or what we call the mechanism behind how this enzyme actually functions. And we do know that enzyme alter the rate of reactions. Basically, the word alter here is mean increase. Okay, enzyme increase the rate of reactions by highlights lowering the activation's energy necessary to initiate a chemical reaction. So in activity 4.3 now, okay, so sketch on figure 4.3 to show the activation energy with the presence of the enzyme. Always remember, the reactions that without or with the enzyme, you won't change the overall energy change. Means that the reactants and the product will have the same level of energy, but what we do here is to lower down the activation's energy only. Okay, as I said that let me use a different color here. So this is the reactions that without enzymes. So with enzymes, you can see that this is the original activation energy that without enzyme. Okay, so when you sketch on this diagram, so energy level remain the same. Okay, and then lower down. Okay, just follow. So now what is the EA? Activation energy with the presence of the enzymes. So this is the EA with enzyme. Are you clear? Clear? EA with enzymes. So you can see that this is the the energy, activation energy is lower down. Okay. So I say that in this case, okay, when substrate need less energy to react because the activation energy is lower, the larger fractions of the substrate reacts at any particular point. Okay, so as a result, the rate of reaction is higher in the enzymatic reactions as compared to reaction without the enzyme. So this I always say that this is activation energy or activation energy barrier. So similar to, I say that the passing mark is 95 marks out of 100 marks. So means that not many manage to overcome this activation's energy. But if I say that now activation energy is lower or the passing mark is lower now, so more substrates or more reactant will be able to overcome this activation energy barrier. Therefore, they form products. Okay. Now, always remember, we say the enzyme lower down the activation energy, but highlight they have no effect on the overall energy change, means the delta G. So basically, if you go back to this diagram, you can see that the energy level of the reactants and the products still remain the same. As long as the energy level of the reactants or substrate and the products are remain the same, then therefore you won't change the delta G, or means that the net energy change. Okay, you won't change this. So when you draw the diagrams, therefore you have to make sure that the energy level of the substrate and energy level of the products must remain the same. What make the difference here with or without the enzyme? Basically the activation's energy. Okay. So next part, we're going to look at this. We always talk about enzyme lower down the activation energy. So how enzyme actually lower down the activation energy? We're going to discuss it now. Okay, so enzyme use a variety mechanism that lower down the activation energy and speed up the reaction. For example, first thing, okay, they form temporary bond. Okay, second mechanism, they do the stretching on the substrate molecule towards its transition state form. And some enzyme, they provide a microenvironment that is more conducive to particular type of reaction. For example, if the reaction requires the acidic conditions, then the enzyme actually can provide this microenvironment. Or in this case, amino acid in the active site directly participate in the chemical reactions. Always remember now, guys, we always say that enzyme, they do not participate or react with the reactant, which is not totally correct, this statement. Because during the process of the reaction, actually enzyme do involve in the reactions, okay, or directly involved in the participate in the chemical reactions, but at the end of the process, they do not undergo chemical change. Means that initially, this is my enzyme. At the end of the process, this is my enzyme as well. Are you clear? Okay, so means that I involve, but at the end, again, that's my original state. That is means by the enzyme. Okay. So first of all, we look at how temporary bonds can be formed. So temporary bond is formed between the substrate molecule and the R groups of the amino acid that make up the active site. Okay, so when two or more reactants, the active site provide a template on which the substrate can come together in the proper orientation for the reaction to occur between them. So this is very, very important, guys. Okay, you try to imagine that we talk about the effective collision. When effective collision take place, we want them to collide at the correct orientations, correct or not? Okay, so now look at this. Sorry, this is my substrate number 1. And then I have substrate number 2. So substrate number 1 and substrate number 2, they have to collide each other so that they will be able to form these bonds, correct? Again, distort and overcome this activation energy. But most of the times, the orientation may not be correct. This one can form the bond, but if the orientation is not correct, then no bonds can be formed. Correct? Okay, between the substrate 1 and substrate 2. So how to make sure that this reaction actually take place in the correct orientation? Enzyme do have the active site. So means that if let's say this is my enzyme, okay, if the enzyme have this the shape of the active site, then I can hold the two molecules at the very precise order or orientation, allowing the bonds to be formed. But in order to hold it, because sometimes you don't, you try to imagine that both of them may not enter into the enzyme's active site simultaneously, correct? You try to imagine I may have the substrate number 1 enter first, and then substrate number 2. So it means that we have to hold the substrates, correct? If you don't hold the substrate, what happened? The first one enter, the first one leave, and then the second one enter, second one leave. So forever you won't get the reaction because we have to wait both of them enter at the same time, correct? So if the first one enter already, we form temporary bond. Okay, so how the temporary bond can be formed? For example, in the active sites here, you have the R group with, let's say, for example, OH. Okay, so then substrate here, let's say the chemical structure of substrate, let's say, for example, this is substrate, this is enzyme active site. So substrate here, okay, have the H. So let's say, for example, H here is delta positive, this one is delta negative, then they can form this temporary bond, which is known as the hydrogen bond. Or substrate is positively charged, R group is negatively charged, then therefore they can temporarily hold the substrate. So normally these temporary bonds, they are hydrogen bonds as well as the ionic bond. So both substrate and enzyme now can hold, again, the enzyme can hold the the enzyme can hold the substrate temporarily by forming these temporary bonds. So therefore, it provides the proper orientations to make sure that the enzymes, the two substrates that will be able to form the bonds. Okay, clear or not, guys? Okay, so this model actually is described by the lock and key model. Okay, lock and key model, where we are going to look at how the shape of the enzyme active site and the shape of the substrates, they are exactly complementary each other. So therefore, we will be able to hold them in the proper orientation. Okay, and so in some of the enzymes, so the active site enzyme clutch the bound substrates. Therefore, enzyme may stretch the substrate molecule towards their transition states form. Now, what does this mean? This is actually explained by the induced fit model. Now try to imagine that this is the enzyme. Okay, then this is my substrate. So for substrates, okay, to enter, okay, draw it this way. Okay, so this is substrates, this is enzyme. Are you clear? Okay, now you can see that the shape of the substrate is complementary, but not exactly. Can I see that? Not exactly complementary. So means that when it fits inside this, it will cause the enzyme to slightly change its active site shape. So it means a flexible, and then substrate can bind. Are you clear? So, but the thing here is something like this, guys. If you stretch on it, so this enzyme active site actually exert the force onto the substrate now. So we'll try to imagine that, okay, when this enzyme active site exert the force onto the substrate, it's going to weaken some of the bonds. So make sure that the bonds can be broken down. Therefore, it push this reactant towards the transition state. Are you clear? So as the active site of the enzyme clutch on the bound substrate, the enzyme may stretch the substrate molecule, okay, towards their transition states by distorting the bond inside the substrates. So therefore, reduce the total energy that must be absorbed to achieve the transition states. So we do know that if we want to break the bonds, we need to absorb the energy. Let's say without the enzyme, the energy involved here is 1,000 unit of energy, which is impossible to achieve, for example. But with the enzyme active site, exert the pressure or exert the force onto the substrate, then now the energy involved to break the bond now may be reduced to 50 units out. I mean, compared to the previously 1,000, now 50 units only. So with this low energy requirements, therefore, reactions can actually take place. So this one actually will be explained by induced fit model later. Okay, so the first one actually is a lock and key model. So which we're going to learn about these two in detail. So highlight, guys, in our syllabus, we need to actually focus in the statement number 2 and statement number 3, how the enzyme actually lower down the activation's energy. So the first way to hold my substrate molecule so that they are in proper orientation for reactions to occur. Second way is we use the enzyme, so the enzyme actually will clutch, okay, onto my substrate, then weakens and distort the bond so that the energy involved to break the bonds can be lessened. Okay. So we do have other way to actually lower down the activation energy. For example, active site may also provide the microenvironment that is more conducive to a particular types of reaction to take place. For example, when the active site has amino acid with acidic R group, then we know that the COO minus. So this acidic amino acid may facilitate the H plus transfer or the proton transfer to the substrate. Can you see that? So the H plus can bind to the substrate, okay, because of this acidic R group, the interaction there. And sometimes amino acid in the active site can directly participate in the chemical reactions by forming the brief covalent bonding. So can you see that they actually involved in the reactions, right? Okay, but the subsequent steps of the reaction restore the site change of their original state. Now, what does this mean? I use a very simple example here. Okay, so let's say this is my substrate molecule, substrate number 1, substrate number 2. Okay, so this is my active site. What will happen here is substrate number 1 form covalent bond first with the R groups of the amino acids. Substrate number 2 form the bond. Okay, so this formation of the bond allowed the new bonds to be formed between the substrate number 1 and substrate number 2, when this bond already done, this one done already, then we break this bond. Then we release the product. Okay, so this is another way we can actually lower down the activation's energy. Are you clear? Okay. So, but for all mechanism, always remember, enzyme only increase the speeds of the chemical reactions without undergoing any net change after the reaction has completed. This is very, very important, guys. Always remember, even though they participate, no matter how they participate, at the end of the process, you can see that product will be released, enzyme will return back to their original state. Okay. So with this, I've done the mechanism how the enzyme lower down the activation's energy.